Hey, good morning, everyone. Sorry for the technical difficulties. Um, Again, when you ask me a question, make sure that I repeat it so that everybody can remember whatever the question was when you view the video after the fact. Um, the exam will be done on Wednesday. I apologize. So, yeah, I have extensive notes, but what we're going to do now is second. I just have to get my colors straight. Is talk about control systems. And the math should look, pretty familiar. Right? And in fact, right, it's going to start with signal flow diagrams, very similar to what you're saying. Have seen, excuse me. Which, yeah, if we just put an op amp, bless you, we have the minus, actually, I'm going to do it backwards or a little bit differently. Right. We have an op amp, which is a summer and some transfer function, right? Which can be something DC, integrator model, low pass model, first order, low pass, second order, right? And this is the transfer function of the op amp, and the G of S in this case, right, is just beta, right? But there can be inductors, capacitors in this feedback network. So, inductors and capacitors have a frequency dependence, and so then you would just call it G of S. And so an op amp is a control system, right? And all the things that we've studied so far, the control systems are something what is known as they're in control. And I'll explain that in a little bit. But when we say control systems, we actually are talking about automatic control systems. And now this H can be any physical system. And the G of H, right, will be some kind of feedback, which in general is some kind of electrical network. All right. And yeah, that means is if this is some physical system, you might have to convert sensor data, right, to an A to D, through here and coming back, right? So really, what was great about op amps is everything was electrical, the signal was the voltage, and we didn't have to worry about anything moving or breaking. All right. But it's a physical system. And then two, just want a little more flow here. Okay. This is how the book does it. Okay. But many times they have the control system like this. You have the summer, which, yeah, nowadays is going to be some kind of electrical thing, right? Then you have I'm not going to label that just yet, but the control system. Okay. Then you have H of S, which they call the plant, right? That's the thing you're controlling. Then you have the feedback, right? And then you have the input. And this, I'm just going to put some symbols, can be K, which is just a proportion, right? It can be K divided by S, which is an integrator, and it can even have, I'm just going to put it in red so you can see it, SK, which is a derivative. And you can have all three, right? Called PID. Proportional is K, integrator is integrator, and D derivative is derivative. And yeah, they would all have different constants. And then this term here, normally we, with the filters, right? When we were doing filter, oh, that would be the low pass, and this node was the high pass. Well, now this has a new name too, and it's just called the error, right? And what you're trying to do is you have an input and an output, and you're trying to set that output to a value and have no error, right? So some examples of that are, the air conditioning or heating in your house. You want to set it to a temperature that's comfortable, right? Varies from person to person. Let's just choose 70. Change it to 70 degrees on your dial or your Nest or whatever, right? And then your house goes to 70. And when the setting and the house equal, the error has dropped to 0, right? But if the house is cold, right, it's got to warm up to it, and the error will decrease to 0 from and if your house is too hot, well, the AC turns on and brings it down. And a cruise control, you set your car's speed, right? And as soon as the speed is what you told it to be, then the error is 0. Now, yeah, the thing with electrical, right, is this input is like a voltage, and we put in a 1-volt step function, and then a 1 volt comes out, but transformed somehow, right? So there can be a lot of 70 degrees to some electrical, to a temperature measurement, to an electrical signal. There's a lot of conversion going on, right? Ships use a form of, it's probably more advanced now, but use an advanced form of PID controller to go from one point to the other. And you might just think, well, aim and go, but ships have a lot of mass. You have currents inputs one way, winds inputs the other way. And so it's better just to tell the ship where to go and let the ship figure it out with PID. Now, at the time, this was controversial, that there's no way a machine, can do as well as a sailor feeling the waves beneath their feet and the experience, right? And so, there was probably all these things about how PID was going to put sailors out of business, but let's not kid ourselves. More manufacturing jobs have been lost to automation than any outsourcing. So the trick for us is to be the ones doing the automating. Okay. And by that is like you're all been doing filters and things like that and kind of by hand, right? You've all used the analog wizard. But let's say now you're doing something more advanced that there's no analog wizard for it. Yeah, you probably should write a Python program so that all you got to do is enter in the constants and the conditions where it'll calculate everything you need so that you can design things faster. If you don't automate your tasks for your benefit, someone else will, to your detriment. And yeah, anyway, so yeah, now the current thing is AI. And really, that's just another automation thing. We've been automating our tasks since Spice was invented. LT Spice is automating tasks, and even let's see, you guys now are using TI microcontrollers, I think, right? I had somebody from a microcontroller company tell me that the C compiler has 30 years of experience compiling code for that particular, optimizing machine code for that particular microprocessor line. And that it will be very hard for you to use assembly language, which is a very low level language, to beat the compiler, right? So C compilers are automation, right? That being said, I think AI is a little bit over promising right now. Anyway, who thought we could get into a political discussion in 110, right? Anyway, so I've given, samples like heating your car, elevator, there's elevators, but there's so much of this in the manufacturing I see you. There's so much of this in the manufacturing process where everything is automatically controlled. Even the reading head on a hard drive, of course, is automatically controlled. And it's got a mass. It can be modeled as a mass spring damper system, all right, as to try to make sure that the head goes where it's supposed to go, all right? But a lot of these physical systems are what we would call out of control, which I'll explain in a smidgen.
So, like, do you think that it would be more used for like analog circuits like perceptrons? Because in the video you said, the guy said that ChatGPT is basically just perceptrons connected to each other. Do you like literally it's just like logic perceptrons, or is it just digital?
So, yep, we have stated that there's big relationships okay? And we are paying for a chat GPT that should not be stealing your data. If you use the free one and you want help writing your 100W report, when you finally get it, because how does it work? You say, you give it a prompt and it comes back. And it comes back most likely mostly garbage. Then you refine the prompt and and then it might get to a point and say, now I'm going to finish it off, right? So in that process, there is your 100W report where you're kind of giving it your stamp of approval because you stop telling it to get better, right? What they're claiming is that with the one on campus, your data won't be used for commercial purposes. And that's all I'm going to say. So, well, I'm a very suspicious person, and like once your data's out there, it's out there. Now, yeah, this is coming from somebody who any video I make it, people can scan my stuff and all of that. All right.
You know, if the school is looking to be running with local,
Hmm?
servers and website?
Oh, wait, how are they running it?
No, they consider looking to run local servers.
Well, this is the AI from the CSU is like a CSU package they bought, and they probably have servers, I would hope, that are locally controlled, but they're probably in Utah. Like my PeopleSoft and all that, I heard the servers are in Utah. But, with VPNs and security and all that, I've never heard of a data breach on like, your grades and things like that. Does that answer your question? Okay. Yeah, but the thing about AI is it can be really useful to sort through data when you quite don't know what you're doing. And that if you take a satellite image and now with so much data and you're trying to find the thing you're looking for, right? And you're just looking one bit. That's how it used to be done. They would make big blow-ups and the operator is just looking through. Well, now AI can say, I think there's something going on here, and then a human would go and say, oh yes, that is actually something I'm looking for. So it's a way to sort through the data much quicker, right? And so yeah, for like a very specific task, right? Um, that that's what I think it could be good for, right? Um, the trouble with your 100W reports is there might not be enough to train the model. Even though, right, I mean, you'll probably have 500 people taking it at any given time, right? So, but it could get you helping, right? And I've used it like on my Google, it'll tell me I'm looking for something, and then basically it's telling me something that's already on some data sheet, right? And then otherwise it's like, how do I do this? Well, turn your computer on and search for it. It's not that bad, but sometimes I get error messages I get messages like that. Okay. So anyway, this is control, and yep, it's automatic. It's embedded in everything we do, and it's more efficient to do it electrically than any other way, right? And that's why controls is like in the EE domain, right? I thought I had it in my notes somewhere. I'll have to hunt up a picture. Notes. That's the midterm. So other ways of sending a control signal, one way was vacuum pressure, right? And in older cars, right, that's how you did it. And when the car wasn't working, it was always a vacuum leak. And and the car is running terribly. You think it's about to die. And oh, no, there's a vacuum leak. So the whole control system isn't working, right? And by the control system is you say how fast you want the engine to go and it goes, right? But also those engines, the way let the gas in, ignite the gas was fixed. You could not change it on the fly, but with variable control timing and electricity, you can do that all on the fly, right? So you can get much more efficient engines than you used to, right? But now things that aren't control systems, right, are your barbecue grill. You turn it on. Yes, I have a knob. I turn on the gas, but how hot it gets depends on how hot it is outside. It's called open loop. And if you were looking at and it'll settle to a temperature, but really that's just because the heat leaving is equaling the heat coming in and it's stable. But there's no feedback, right? It's not automatically adjusting the input for any thing, right? Um, and so what I want to do today is kind of talk about systems that are in control, right? And what that looks like. And then next time here are systems that are out of control and how to fix it. But I'll give you a preview of that. So if I have a system, okay, all right, this has a pole at +1, right? What makes this go to infinity? When s equals 1. Okay. Well, if I take I'm just going to take the impulse response, which is just the inverse Laplace transform of this, right? It's e to the plus t. So over time, right, this system will exponentially grow, right? And the thing is the Laplace transform has always had that, right? Because really, when we showed like 1 over s plus a, right, the inverse was always e to the minus at, right? But we always kept that number positive, and so it always, and I'm leaving out the ut, right? It decays to 0, all right? So that decay to 0 is actually because it's in control, and it's because the pole is on the left-hand side. Another system that we didn't talk about, right? And I'm just going to say a s squared plus a squared. All right. When I find the poles of this, I get them purely on the imaginary axis, which some folks might have been talking about 112's exam before class started. All right. Now again, in 112, it's all about the unit circle. 110 analog, it's all about are the poles, is the real part all negative? All right. Well, this, right, is a sine wave generator. So it's not, it never settles, right? An other system that we've been talking about, in fact, the only one that's kind of really been out of control, I just never mentioned it, right, is 1 over S, okay, which has a pole at 0. And why is that out of control? Well, let's do a step function, input times the integrator, ramp t, that never settles. It keeps going on forever. And you have already seen in lab I'm not doing it exactly the way I do it in the notes because I just want to make it easier to draw. All right. You've seen a filter with 3 integrators, right? And then I have A1, A2, A3, right? And then minus, 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 input, and output can be on any one of those nodes, and those are all filters that are in control. All right. No matter, you can have a step input, and this output will settle to a constant value. So taking something out of control, putting it in a feedback network can make a system in control. You've already been doing it. I just felt that it wasn't the time to mention it due to cognitive load theory.
Just, so you asked us to answer like, solve for the transfer function, right? You just solve for everything pretty much? Or? Yeah. I just take a little bit of that.
This particular thing,
Yeah.
right, is to tell you how to design that filter. And it's called, in the book, it's DF2. Other people call it state space. So I'm not going to have you come up with it, right? That question, what I'm trying to tell you is you've already been kind of working on this, right? And so even though now we're entering the last third of the semester, everything you will have seen before, right? And you just have to add to it. And like I say, 110 is about 5 concepts that are all hard, but once you get it, then everything makes sense. Where 118 has 1,000 easy concepts that you have to get 100% right, or it falls apart. All right, so it's 2 different ways of studying. 112 is probably more like 110, right? but yeah, like if you, like what's the problem with 110? Let's just say we have a graph of effort, your effort, right? And then grades, right? Ideally, we would have this 1-to-1 ratio, right? I don't mean to go down there, right? And yeah, some of you probably feel like on any given day, that's what's going on, right? I've been there. I remember being there, and that's why we have, the final exam the way it is, so that by the end of the semester, yeah, things are starting to click. Okay. Anyway, oh yeah, just so the question was, would this be an exam question, like find it or derive it? No. But in 132, probably. But they would have probably something not like this. Okay. Um, okay. So we have all these Jupyter notebooks. Now, yeah, I know everybody's busy, right? I created these notebooks so that you could have some like real world math examples and play with it. I see you. But if you really want to learn it, you should make your own notebook and then put it on GitHub and then make a LinkedIn account. To study for this course, I made these helpful tools, then mention my name so then I can say great job or something. At least like it.
Oh, I was looking at the controls and feedback. So
Back
any
back here.
yeah. So would you say any control system with a negative feedback is always in control? Or it's not like not always the case?
Okay. This system is out of control. I can put it in a feedback loop to make it in control with a constant, but that constant will have to be above a certain value. So just because the negative feedback is there doesn't mean it'll be in control. You have to apply it properly. Now, yeah, op amps, right, have that negative terminal. So you think, oh, I always have negative feedback. But the transfer functions are complex to say the least. And there will be a frequency at which, if not designed properly, will make it positive feedback. And so if you are designing the op amp, right, you're doing the chip, right? You have to make sure that when you're setting that gain bandwidth, there's a phase component that you have to keep to below a certain value. Otherwise, also sometimes it can be stable and then your feedback network makes it unstable. And if you look at and I'm going to leave it there. I don't think what it is in 98, we start off with how to use it in a simple fashion. Then we start peering under the hood in 110, more complicated examples, more detail. 122 is even more. And then 124, you're looking inside the op amp, right? 223, you're designing the op amp, all right? Now that I remember your AI question, yeah, so in order to write an AI prompt, even for digital design, I have discovered you have to have at least at 118. Otherwise, you don't know. Because I had freshmen, they wanted to do it. All right, let's try it. Oh, it all just blew up in our face, right? And then I had somebody with more experience, and they were able to monitor the prompt for correctness. And analog is even hard. So to understand like chip design, I've already laid out, it starts at 98, 110, 122, 124, and then a grad course. Okay. So I'll leave it there. That was a good question. Let's come back. So again, you now, normally I've called this H of S, but now it's called Q of S, which is the original system, right, of H and G, right? And it's the same thing that we've been doing with the op amps, right? So I'm not going to derive that equation. And again, this is a simple, it's the simplest control system you can have, all right? But if you're, like when it comes to 132 or more advanced things, right? Oof, that color. Okay. It'll look like more like this. I'm just going to say K, KS, or K divided by S. Some combination, okay? Then the system, and that's whatever the output is. The temperature, the speed, the location, right? Oop. I mean, you think about it, I don't know, that's my SpaceX rocket, which can land on its tail, right? The first thing you learn in control theory is that if I have a mass and a rod on a pin, that this is completely unstable. It's like any little noise will cause this to fall, right? So they are having very complicated control systems to land it. But what you don't realize is it's unstable going down, it's unstable going up, and you need control systems to keep it flying straight. It's not just like a toy rocket with your nice fins, right? So this would be, and then they would call this the error in time. I don't know, they put error T, even though we're doing everything in the S domain. But again, you're measuring everything in time, all right? And so let's say I just took this, right? Out would equal, I'm going to just choose this one, K HS, right, minus out. Bless you. Oh, sorry. Minus out K HS. Okay, that sounds good. So then I have out 1 plus K H, right? And yeah, because of that negative feedback, when I combine the terms, it goes positive, right? Just let me finish so I don't lose track. Then out over in would be K HS, right? 1 plus K HS, which, I don't know. Yeah, all right, so what's different here is that we have G of S, H of S, 1 plus G of S, H of S. Whereas before, we just had H of S divided by this term. Now, yeah, if I start taking it off of that node or that node, I can find it, but, so it will look a little different, okay? But, I do it in this class. Oh no, I have it in picture form. I do it like this. It will always be like this. But what I'm saying is it won't always be like this. Okay? But, you know, anyway, we derive it out. And then in this example, we have, I'm just saying, oh, it's proportional, right? That's the K we're talking about. So now here's my example. Q of S, H of S, I have this is K. G of S can be K, SK, or K divided by S. And H of S is 10 divided by S. It's an integrator. It's out of control, right? Because integration, if you put in a step, the output will never settle. Okay, so now so here's my 10 divided by S, and then I guess I put it, you know, backwards. Usually I put the 1 here, right? I expand, and I have 10 divided by 10K plus S. All right. To answer your question about is it always stable? Well, if K is 0, well, I get 10 divided by S. It's unstable, right? If K is negative, it's unstable. So K has to be greater than 0 to make sure that you have a pole on the negative side. All right. And this is just me trying to see how useful symbolic math can be. Because once you do it, then all of a sudden it's like in your head and you almost don't need it for these examples. But what I think is if you're doing something new, start with something simple, get it working, then, and it's like so complicated you can't figure it out, you know, in a reasonable amount of time, then yeah, symbolic math is probably pretty good, right? Anyway, then I give other examples. Okay, but so I wanted to talk about systems that are in control. All right, so I look at H of S, and what makes this go to infinity? S negative 10. It's on the left-hand side. So when we take the inverse Laplace transform, well, it's right there, right? Minus, you get minus 10 decaying exponential. And then when you do the step function, yeah, it's 1 minus that. So it goes to 1 because the exponential decays to 0. Okay, so it's stable. Now, this red is the unit circle, which, I don't know, it's kind of annoying because we're not really trying to be on the unit circle. But here's the pole at minus 10, right? And this is a program called LCAPI. It doesn't come with Colab, so you just have to somewhere, I say, install it. Okay. And then it does the Bode plot. Now, yeah, this is in radians, not degrees, and I couldn't fight with it anymore. But the phase goes from high to low. It doesn't matter if it's at 180 or 90 to 0, right? Or the phase is going down. If that phase is going up, that system is out of control. And here's the thing, you can never measure a Bode plot for an out of control system. Because as soon as you put anything in there, it'll oscillate, go high, go exponentially negative. So yeah, that Bode plot will only exist for in control systems. All right, and then here's a step. It goes to a constant value, and then the impulse response decays to 0. Voila. High pass. In and out, in and out. I think that, all right, so here, that probably needs to be fixed. No, that's right. I can see the S. Let me see, maybe I should zoom in a bit. Okay. So now that's a high pass filter, right? We have S here. At low frequencies, it drives it to 0. At high frequencies, drives it to a constant. We take the inverse and we get a delta function. But that goes from 0 to infinity back to 0. So it settles, right? And then we have a minus term, but again, decaying exponential, right? And when we take the step response, we get the decaying exponential. So really, to me, the best test of whether something is stable or not is the step response. Because if it goes to a constant, it's constant. It's stable. Going to a positive constant, negative constant, or a 0 constant are all stable. Now, yeah, you might oscillate a little bit on your way, but it's still in control. So here we have the pole is still -10, and we have a 0 at 0. But again, control is all about the denominator. Here's our Bode plot. Notice the phase goes from high to low. All right, step response decays to 0. Impulse response is, that 1 is really like scaled by 1, but it really is infinity. So it just doesn't look quite right. So you see this little delta function here, and then it goes to -10 and decays to 0. Second order low pass. Okay, let's try that. Okay. Now, I don't have it in pole 0 format. I have it in the kind of get it ready to take the quadratic equation format. So I have 2, right, times the damping coefficient times omega naught, right? And then here's omega naught squared, and it's low pass because omega naught squared is there. If I let S go to 0, you got 100 divided by 100, it's a constant. And then when I let it go to infinity, it goes to 0. All right. Now what we're going to find is that I'm getting a pair of complex poles. But look, no, you can't see my finger in the video. Look, the real part, right, is negative. All right. Now, yeah, there's an imaginary part. That's okay. It's still negative. Look at the Bode plot. Yes, there's a peaking here, which means when you do the step response, it might oscillate a bit before it. Sorry. So if I take a step response, right, normally you're used to seeing that, but that peak will cause some oscillations before it settles. And yeah, if it takes it could be theoretically in control, but that settling time could be longer than you want, and you still need to fix it. Notice, phase goes down. Oh, step response is right there, right? So I chose one that was really oscillating quite a bit, right? And then there's the impulse response, but they're decaying to 0. Now, yeah, maybe 4 seconds is too long. I don't know. Second order high pass. Now we have S squared. Same denominator. So what changes? The poles are in the same place. Well, it looks like they moved a bit. I don't know. But notice I have a 0 here and the number 2. That means there's 2 zeros there, right? Well, it's a different plot because the peaking here is different. So I've chosen different values. Still, phase goes from high to low. The step response, yeah, it detects the edge, but it oscillates before it settles to 0. All right. Where the high passes we've been looking at usually are just right around the beginning, and then it settles to 0 without any oscillation. Bandpass. We have not really talked about bandpass, but that's a filter that is trying to keep a small range of frequencies. All right. So here, what's different? The numerator. So what kind of filter you have is the numerator. Whether it's in control or what are the poles or the dampening coefficient is all the denominator, right? So now I've kept it to where the poles are still complex, right? But the real part is 5. And notice the 0 is here, but there's only 1. The Bode plot is very selective at that frequency, and the phase goes from high to low. And it looks almost like the high pass. But notice the high pass went straight up and then came down. Look, it's taking time to climb, and then it comes back and settles to 0. All right. But yeah, the impulse response, here's the high pass, right? S squared 2 omega naught damping S plus omega naught squared, right? The step response kind of turns this into S squared plus da 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 da. But the band pass, right, is already 2 damping omega naught S. So if you're wondering why does the step response of the high pass look like the impulse response of the band pass, right? It's because, yeah, it's 1 term of S in the numerator. That just came to me. The notch filter, you're trying to get rid of frequencies. And we've talked, you've worked with it a little bit, but we're adding the high pass and the low pass. Right? So it's really parallel combination. We have a low pass and a high pass, same denominator. And now look, we have the same complex poles, so it's going to be in control, but the zeros, there's 2 of them, but they're actually imaginary, right? That's okay. And then this is the Bode plot. Now, yeah, you might say, well, how do I interpret that phase, right? Well, this is just ignore the middle part. Notice the phase is going down, then it comes up, but then it's going down. It's in control. And you get this weird shape. right? This is the step response. And notice, it's giving me almost a high pass and then a low pass. And in the middle, it's in the middle time, right? That's why you're getting rid of that middle frequency. We're going to find out that by going from 0 to positive time is the same as going from low time becomes high frequency, high time becomes low frequency, and you flip it for frequency. Okay. Still, it's a regular, it's not a 1-to-1 on the Bode plot, but I'm just saying, see this is 2 seconds. That means at low frequencies, it's going to be passing. At 0 seconds, it's almost passing 1. So at high frequencies, it'll almost pass 1. Joe?
If you had a Bode plot where it dipped down V shape and came back up, would you say that's in control? Does it just matter the start point and the end point, or does it matter the slope of the Bode plot? And this is just a shift, so it's okay.
I know that I've done things where the phase goes up and down, and that doesn't work. I don't think I've tried that. I don't know. That's a good question of whether is it really where, because in this one it starts and ends at the same place, but it's except for that. Now you know what? I think it's somewhat of a misinterpretation of what's going on. That phase. And it really should not do that. But it takes a bit of manipulation to get it to, like you have to know about it ahead of time. I think though LT Spice does the same. But it just, I don't know. What I would have to do is like, all right, what would cause the phase to do that? And then do a Bode plot and then see, and then take the step response of it. I don't know.
So when we're looking for whether the system is going to be stable or not,
Yeah.
should we look at the phase first, or should we look at the poles first?
You are going to look at the polls. I'm giving you a background, but I don't believe I have any questions. Here's the phase. Is it in and out of control? What I'm trying to do is like you're trying to see and link it, right? That's what today is more about. But the question really is, here is a system out of control. Why? Or maybe this is better to write down. Okay. You know, S minus 1. Y out of control. All right. Pole on right-hand side. I do second order on the exams, so you have to use like the quadratic equation. Okay. All right. What does it look, what does the time look like? Oh, something going up. Now it's a high pass, but like it's going to go high, it's going to go exponentially low. It might do something weird like this, but really, you just want to say exponential growth. Now, right, just so you know, why is it out of control? Pole at 0. What does it look like at time? Step response gives it a ramp. Literally sketching it like that. All right. Then do a control system, the simplest control system to fix it. Okay, so then you have S minus 1, Now I'm just doing circles, okay? G of S minus plus and the summer. Okay. So then you have S minus 1. It's this 1 plus G of S minus 1. Okay. Then you have S minus 1. Then here you just have plus G of S. Okay. What G of S will make this in control? Well, this is the problem, right? So G of S actually has to be K divided by S. All right. Now K divided by S gives me that. All right. Now I have a constant. What should that constant be? Well, it has to be what? Bigger than 1, right? K has to be bigger than 1 because I'm summing. And notice it's in this system, you kind of started with an out of control high pass. Now you have an in control high pass. And so coming up with the right equation, G of S equals this. What are the conditions on S? That is the exam problem right there. Except it'll be second order. And you have S. I'm just going to call it, you could for the numerator, you can have like something like AS squared. And then in the numerator, right, you can have B can be missing or negative, and C can be missing or negative. Because in second order systems, missing or negative is definitely out of control. For third order systems, you actually have to do it out. Like what are the poles? And then fourth order, yeah, there's not there's a process. Right, what is it, Booth or something? Don't do Booth on the exam. Just do it the simple way, right? There's a process to find it, but part of that process is, let me sweep K to see what happens, right? It's called like a Nyquist plot. Okay? 132. Now, yeah, I have 3 homeworks designed to get you to that point. To this one or? All right, so
Yeah.
this bit.
Sorry, I missed. Can you explain why you want it to be greater than again?
Well, let me, that's a good question. Why did we want K to be 1? Well, let's look at it graphically. Okay. We had S minus 1. All right. We had a pole here and a 0 here, right? So this is on the right hand side, which is going to give me positive in growth, exponential growth. It could be positive, it could be negative, but it's out of control. So we need to push this over here. So I'm just going to go straight to the equation. I have S minus 1 plus K. When I used K divided by S feedback, I was able to fix it, all right? But now, the pole equals K minus 1. Well, I need to get it, so if I wanted to put the pole here at 0, oh, K equals 1. 1 minus 1 is 0, but that would make it an int. So if I did that, right, you know what if K is a half? K equals a half. Then I have S minus 1 plus 0.5. I'm just going to do the numerator. I have S minus 0.5. Yeah, now it's S minus 0.5 t. It's not as fast exponential growth, but it's still exponential growth. What did I say? Yeah, you're right. Wait, no. Wait, hold on. You guys are confusing me. S minus 0.5. Oh, right, positive there. Sorry. All right, now K equals 1. Again, I'm just doing the denominator. S minus 1 plus 1 gives me, this is kind of a bad example because I have S here, and then I would have S over S, right? Which means it's not responsive to the system at all. I guess that's a whole other control thing. Whatever you put in, nothing happens. And we all know people like that. How do we get it? If K is bigger than 1, and now we'll just do K equals 1.5. Okay. S minus 1 plus 1.5 gives us S plus 0.5. Now it's here. We get exponential decay. That was a great question. Yes, sir.
The pole be at 1 minus k, not k minus 1 for that example?
Which one?
Or go a bit to the right, not,
This?
not the left,
In the middle,
in the middle.
where you say pole equals K minus one.
Yeah. Shouldn't it be 1 minus k? Or am I wrong?
Doesn't say anything. It's the end of class and my eyes are spinning. I would ignore that part. But what was I doing? Was it K? I had examples. K equals 0.5, K equals 0, K equals 1.5. This becomes S, so I'm just going to write S minus 1, and this is just the denominator, right? So here, then I have plus 0.5, oh no, K is 1, K plus 1, K plus 1.5, and then the pole becomes, it's on the right-hand side of 0.5. I mean, it's a negative number. The pole goes over here. It's backwards, right? Then this just cancels out. You have integrator, and then here you get the control systems you're used to. So whatever I wrote, you can just let that go. But thank you for letting me know it was confusing. Okay. All right, everybody. So I'll see you. Good luck on your 112 exam. I'll see. Not that you need it. See you on Wednesday.